Today, we will continue with our topic of our second type of predictions that we can make with this quantum theory that we've developed, namely the theory of bound states, some predictions that we can make for so-called bound states. I will remind you briefly what exactly we mean by those, but the key point is that we are now expecting to find discrete, not continuous energy levels. So what we were doing last time, and we will wrap that up this time, was just discussing some of the general features that are a little bit different when you are looking at the energy representation for a set of discrete energy levels as opposed to a set of continuous energy levels, so that we will know what to do with the solutions that we find for bound states once we are able to obtain them. We will then wrap those up, and we will then begin our first real example of bound states, looking at a particularly interesting and relevant application. Now, just to remind you of what we mean by bound states, we are discussing a situation where we would have a potential Vx that might have this sort of a general appearance, but in particular we are interested in the energy levels that we will find when the energy is less than the potential, either out at minus infinity, both out at minus infinity and also out at plus infinity. This would then ensure that I will have classically forbidden regions both to the far left and off to the far right. When we get into this situation, the particle then is generally repelled out of those forbidden regions, even though there might be some quantum tunneling going on, but we do spend most of our time localized or bound to a particular region of space. The interesting thing that occurs then is that the classical period of the motion, if you want to go to our semi-quantitative Bohr-Sommerfeld analysis, the classical period of the motion will be finite, so that this energy level spacing, which goes like h over that classical period, will be greater than 0. This implies there is always a gap or a separation between my energy levels, and so therefore we have a set of discrete states. So when we have that particular situation, this is what we were discussing last time. What, namely, does the energy representation look like in this special case where we have discrete energy levels? Now, in general, we quoted from the quantum principle of superposition. We expect we should be able to write any arbitrary wave function. Notice it doesn't have a time dependence now. I'm just talking about the quantum state at a particular time. I'm not focused right now on dynamics. So I have some quantum state described by a position representation wave function, but I can also write it in the energy representation through my quantum principle of superposition, which would then tell me I can write it as a superposition of these pure states of energy, which would be the results of an energy measurement. Those pure states are with respect to energy, and we of course know that we can find them by solving the time-independent Schrödinger equation, which would give me this set of results here, where the E sub n then are these discrete energy levels we are expecting, and the phi n are the corresponding quantum states or wave functions. In this superposition, what makes it a little bit different is that now that I have a discrete set of states, I label them with a discrete counting label n, and then I have a finite sum. I no longer have an integral. I do write this just right now with this sort of ghost integral symbol here, just to remind you that in general, I might be in a situation where I have a continuum of energy states, or, very interestingly, sometimes I can have a mixture of both. So this sum integral just points out that in general, you might have some part that is a sum and some part that is an integral over a continuum, and you are then responsible for being able to write it as a sum and an integral and knowing how to handle the various situations. At the moment, we're just going to pretend that we're in a situation which has only discrete levels, so we can focus our attention on the mathematics that arises in just the case where we have that discrete set. Now, you may be wondering, what kind of situation would I need to be in order to have sometimes a discrete set of energies and sometimes a continuum set? And my example here illustrates that for you. So notice that the energy level I've drawn for you has this forbidden region, this finite classical time, and therefore an energy level spacing and a discrete energy spectrum. If I imagine what happens as I begin to increase the energy, however, as I move this line up, I will eventually reach feature situation where the particles become unbound, say on the side over here on the right, in which case their classical period, they can extend out to, the particles can move out to infinity, their classical period would become correspondingly infinite, and their energy level spacing would go to 0. So in this case, I would have a discrete set up to energy levels up to about here, and then once the energy just passes over that value far out on the right, I then would go into the continuum portion of my spectrum. Very good. So as we said, though, we're going to focus on a case where we just have discrete energy levels. Now, one of the first questions we can ask of a quantum system is the prime question in quantum mechanics, is the probabilities. So we could ask from this energy representation, what actually is the probability when I'm in this state represented by psi here, or equivalently by this discrete set of coefficients, which now I wanted to point out actually make up my energy representation of my state. So I no longer have like some psi tilde of k, which is my momentum representation. I now have a discrete set of coefficients. These are the energy representation for my quantum state. And given that energy representation, I can ask then, what is the probability of finding those energies? And what Dirac would tell us is that, well, surely it's related somehow to these weights. Larger weights give larger probabilities. And what we had seen previously, which worked out very nicely for momentum, and the general conjecture after you've seen this over and over again is that this also works for all the representations, is that the probability should be proportional to the magnitude of the complex number. So I'm not dealing with complex numbers. It has to be something positive. So it's actually the magnitude squared, but it might just be simply proportional to this. We had a very nice thing happen to us in the momentum representation, though. You might remember that for momentum representation, the probability of momentum k was just the square of the momentum representation wave function. And we're hoping then we might find the same exact equality here. So one question we will be asking is, are we lucky? Do we find what we would really love to find is that this is actually a strict equality, not a proportionality. In other words, that my proportionality constant should just be 1. Now, on our way to answering that question, one of the first things we need to be able to figure out is actually how to transform between our representations. This formula shows me, given my energy representation, given the discrete set of values W, this gives me the formula for finding the position representation. I have to be able to also invert this process. And we had a guess for how to invert it. In other words, how to go from knowing the wave function to knowing the coefficients. And our guess was that it would simply be equal to this overlap of the wave function whose coefficient I'm trying to find with the quantum state whose representation I'm trying to determine. Now, this conjecture comes about just from the same type of ideas that allowed us to prove actually the Fourier inversion theorem. It followed this exact chain of logic. And the last thing we had pointed out was a key fact we will need in order to prove this, which is to answer the question of what happens when I look at overlaps or Hermitian inner products between my different pure states of energy. And we pointed out that that overlap or that inner product is equal to the Kronecker delta, delta sub nm, which is the discrete version of the continuous Dirac delta function. And this delta nm has this very precise definition that if n is not equal to m, I get 0. This is because pure states of any observable have to be orthogonal to one another, which was a theorem that we had proved actually on an assignment earlier on in the course. And in the case where n equals m, we actually get the number 1. To see why this is 1, just remember that when I have phi n with phi n, because n equals m, that overlap can be written, of course, in the traditional format as the integral of psi star psi or the integral of psi squared. But this just tells me, right, when I do a measurement of my generic quantum state, I know I get one of these pure energy states. And this then tells me, once I'm in that pure energy state, what is the total probability of finding the particle somewhere in space? And the answer to that question, of course, is 1. So, where we were going to begin now is to consider how we can actually prove this key result for how we extract the weights, or in other words, the coefficients that make up the energy representation of a generic state psi.